Hey, oh, I see some changes here in layout. I like it. I like how I see my preview. But okay. This is how I used to. Okay, actually, I like this a lot. And since it only will be me today, I mean, no extra coaches for the session. I think I will leave this as it is. So, hey, how are you? Welcome to this Global Hack Week, Data Week. Today we'll be reviewing artificial neural networks. So, this is a very, very exciting session. Um, First, again, I'm so rude. I like to introduce myself for those who don't know me. My name is Alberto, and I'm from Mexico. I'm one of your Mexican coaches. And well, I know this is not the first day at Global Hack Week. Actually, after this session, I will be giving the today in Global Hack Week Day 4. Oh no! After this, we have Rosendo. Sorry, I thought it was just me right after this. But no, it will be the neural network using MATLAB part one, because remember we will have 4 sessions of this, and then we will have Rosendo analyze, query, and visualize graphics session. Check that out. That will be very, very cool. And then coming back with me with today in Global Hack Week Day 4. But yeah, remember you can always watch the agenda, and I will give you the link for that. It's in ghw.mlh.io. And here's the link I just posted on the comments. Nice. So, oh, sorry, I received a bunch of notifications here. Um, yeah, resuming. So, this will be my first session of this Global Hack Week. I am so excited to be back again. I love giving these streams and sharing all these great knowledge. I love to see your enthusiasm and your comments here. So, for example, we have Nihal Kumar saying hello, some rocket ships, Mariasla with a cool kitties. Joro says hi. Alxa says hi. Sheerstrip says yo. Joro sends a purple heart, which is great. Paulina says hello. Hello again. Well, this is an emoji from Joro. Um, Mario Osla says hi. And hello, Kumar says Storm here once. So, this being said, let's start. Let me drink some water because this will be a lot of talking in this session. And let me start sharing with you the uh, the great resource of this. First, I would like to give you this, which is the book in which all of these sessions are based. The name of the book it's called Neural Network Design by Martin T. Hagan, Howard B. Demuth, Mark H. Beal, and Orlando De Jesus. But you can mainly know it as the Hagen neural network design, right? Um, and a repo, and that repo it's from me. Um, Let me share it. Actually, I will give you 2 repos. One I created, and It's containing some of the neural network architectures. I haven't updated with the last ones, but for the one of this session, which it's called the Hami network, you will be all right. So this is the repo, and another repo that I found incredible handy, containing these how to say codes for all the book designs and stuff. Actually, it's this one from the author G. Cass, Jacob Taylor Casati, GCAS01 in GitHub. This is another great thing. The difference between these and mine is that I only have like right now two implementations of the networks in MATLAB. But this one contain chapter 2, 3, and 4. It looks like examples, but in Python. So if you're not a great fan of MATLAB, which I don't understand why, or you don't have a license, because that's another thing. Remember, MATLAB, it's not a free software. But hey, if you're a student and if you're here in the mainly hacking events, you can apply for 3 months, a trial, and yeah, you can check it out. I see some comment here. Hello, I'm sorry I missed anything. You're late. No worries. We were just getting started, and I'm starting to share some of the resources for the sessions. Hey, Abraham Malik says hi. Nice. Good to see you here, man. No, bro, it just started. Yeah, thanks for replying. So yeah, remember, for those who are arriving, this is the link for the Global Hack Week. So anytime you can check out the schedule, the challenges and stuff. This is the book, Hagan Neural Network Design, a beautiful masterpiece when you want to start learning about neural networks. And it's the main reference here for all the sessions, the 4 sessions we will be checking. Repo for that I created, that contains at this point, some of the architectures. Later today, I will upload the other architectures for the sessions. And another repo that helped me a lot creating these, from Jacob Taylor Casati. I think Jacob, it's NASA. I think he works at NASA or something like that. Yeah, that will be all the resources, right? Oh, and a last one. Well, actually, Jacob, it's already referencing this one. Uh, but there's another repo from another author that help Jacob, not me, because I checked more the code from Jacob. But we have this one from Evangelos Stamos, which is another link or repo that contains a lot of work done on this book, on the neural network design book. It can comes really handy for you if you want to take your neural network studies to the next level. I mean, we probably that we don't get a chance to see it, all the content during these sessions, because it will be a lot. But hey, the resource is there, and feel free to check it. Right. So let me start closing all the tabs I have, because it's a lot. Okay, okay. Nice. I see a comment here. Can you share the checking link? Yeah. Oh, sorry, I always forgot about that, and I actually I should check it. Here it is. Oh, Malik, you already shared it. Thanks a lot. I think the easy one can be a little bit more writable. So here it is. Thanks a lot. Coco Sensei 27 says crocodiles. I think that's crocodiles. It reminds me like the Pokemon. So yeah, I will say it's like crocodiles. Yeah, nice. So I hope you checked the links I shared to you. And now let me start sharing my screen. And you should see something like this when you download the book. Just let me change layout. I don't think I love that. Yeah, this one, I think. Nice. Dino, not crocodile then. Okay, no worries. um, this is the book, Neural Network Design. Again, great introduction to neural networks. We will see today in this session quick history about this, just like the basic stuff for those one who are starting, don't know what a neural network is. Actually, I would like to know that. Can anyone be brave and try to explain here on chat what a neural network is? Um, and I want to say something. The proper name will be like artificial neural network, A and N, but that's too long. So we can have a rate to neural networks just like that, and that will be good, right? So we all will understand what we are talking about. Um, so yeah, the introduction, the history, the we will start checking some network architectures. And for this specific session, I want to introduce you to one called Hamming network, which is this one. And you can be thinking like, why don't perceptron and other stuff? But I think I will get the chance to explain perceptron more in the future, since we need to understand this in its whole complexity without even talking about learning. So yeah, a big thing that got me for surprise when I started learning about all of this, because I got it related with artificial intelligence. It's that it doesn't necessarily apply for artificial intelligence. So at some point of neural networks, we can be just doing algorithms um, that classify or then predict data, but without a learning rule, without the algorithm actually do the learning phase of the parameters, we are not talking about artificial intelligence. At some point, actually, in this session, we are not going to do artificial intelligence, because we are going to build the model and build the parameters like manually. So no learning, so no artificial intelligence, right? And machine learning technique that uses AI to teach computers how to process data in a way that mimics neural human brain. Okay, this is a great answer. Thanks a lot for sharing, Shimori, and great to have you around. But again, I will be cautious with the words here, and more when we enter to the artificial intelligence world, because I've seen that there's no consensus about this, but for me, like I think it's again not necessary talking about artificial intelligence when we're talking about neural networks. Neural networks, it's a machine learning system inspired by the human brain. It's made of layers, input, hidden, output layers of connected neurons that process data, helping the model learn patterns and make predictions. It's a big, fancy math functions that gathers better the more you train it. Okay, this is a very long and a very interesting one. And I love the part that it's inspired by the human brain. Yeah. So this is where we get to the first answer that I want to check. The biological inspiration. So let's start with the book, right? We have the preface, knowledge, objectives, blah blah blah, history. Uh, about the history, we just need to say that it was. This is not a new thing. Like neural networks are not a thing that we just invented and revolution the artificial intelligence world. Blah blah blah. No, actually. I don't want to lie. I made an essay about this. Let me check if I can uh, see this very quick, because I even think neural networks were before artificial intelligence concept at all. But yeah, I'm opening a document I have about that. Give me a second. Yeah. Okay. Uh, yeah, artificial intelligence was in 1956 by John McCarthy, and neural networks were, yeah, were before, like in 1940s, 1950s, earliest. Um, I, I have an accurate date, like in 1943, Warren McCall and Walter Pitts published the artificial network, like simple model. Yeah. So, yeah, I just wanted to quickly check because I don't want it to lie. So, yeah, again, neural networks are very, very related to artificial intelligence, but for the moment, I want you to think it as separate things. And if I have to describe it somehow, it will be like a family of human or biological inspired algorithms that can, yeah, that can, but they don't necessarily do it, that can learn how to make tasks. And they have two modes mainly: the predict mode and the classified mode, right? So we have a more complex idea of what artificial neural network is. But let's check another answer. These artificial neural networks are core technique model machine learnings to perform complex tasks. But again, these are great answers, and thanks a lot to reply here on comment section. But I want you to separate these concepts. I know they come together and they help each other a lot. Actually, when we start talking about like deep neural networks, you see that it is a specific area of artificial intelligence, which is deep learning. Uh, but but for the moment, they are not related, right? So we can do neural networks, artificial neural networks, without doing artificial intelligence. And and this is a question, or this is something that frustrated me for a long time because I didn't know how to separate them. Like I always thought they were like the same. But trust me, again, there is no big consensus of how we start classifying something as artificial intelligence. I will say that it depends a lot, but you can do it. Like you can say it's artificial intelligence when you mimic like human capabilities. For example, in the case of neural networks, when you start applying this learning, like doing the learning, then you get artificial intelligence. But we can design these neural networks without doing learning and just have them to process data in an accurate way without learning, like us doing the learning for the network, right? Um, Again, which is what we're going to do right now. So let me check here now that I have this open, my notes of the session. And yeah, so calling back to 19 here, for example, this is the one I was talking in the 90s, 1940s. The work of exactly in 1943, actually, Warren McCall and Walter Pitts showed networks of artificial neurons could, in principle, compute any arithmetic or logical function. So, based on this is the same principle of all the modern computing working. Like transistor, logic gates, etc. Right? With this work, we started putting attention to neural networks. Then, McCall pits were followed by Daniel Hebb, who proposed the classic condition that caused the properties of the individual neurons. So he proposed the mechanisms for learning in biological neurons. So the learning thing here and the possibility of not doing just the manual work, because you will see later that doing the adjustment of the values in the neurons, it's hard, but the value in this is that they can change their values, the internal, and I'm going to talk about complex concepts, weights, bias, connections, transfer functions, and stuff. They could learn how to do them themselves. Uh, I see some comments, and since I watch them growing, I didn't want to miss anything. So let me check quickly. I see some these like ducks. I think we also covered neural networks in AI. Yeah, I'm getting learn a lot about this myself. So as I always say, that the best way to learn something is to share it. So I wanted to talk about this also, not in the AI ML Global Hack Week, but in this data one, because they are so correlated, and I will show you how. Again, the crocodiles, these ones, I don't know what they are. Um, then the octopus. Does your paper discuss the role Alan Turing play in neural networks and computer? I don't think this one does. Or on, I don't remember it, Shimmery. But if you start looking, um, you will see more papers that actually talk about that. But th- it's complex, you know. Again, I write an essay. I can share it with you, but the thing it's in Spanish, and I mentioned, for example, the work and of Alan Turing, but what I found was like more in theoretical idea, like. Um, I have this. It's more focused like for artificial intelligence in general than for neural networks. More in the article, he has an article called something like computational intelligence in the machine. Um, that wants to speculate how the process of thinking can be very big and difficult to define. And that's because of the Alan Turing test. And the idea of a machine can get over that. At That's the idea of, or that was the idea of Alan Turing of artificial intelligence. And if the Alan Turing test was like beat up, that would mean we have a thinking machine. But nowadays, it is not true because we have machines that uh, get through the Alan Turing test and then beat the test, and we know there are not thinking machines because our concept of thinking now it's more robust than the it was before, you know. But yeah, that was a great question. Thanks. Yeah, I agree with that during the more theory that application. Yeah. So let's continue here. Um, yeah, we're talking about the history and how this was invented, but doesn't get you along with a lot of theory and boring and text and not enough code. Think of this as McCall and Pitts invented these first neural networks, right? They invented this first neuron, and let's check that first neuron. Let me get to that. Applications, banking, fans, page, blah blah blah. Yeah, hitting here. I want to introduce you to the biological inspiration, the basis on how these are built. And if you didn't know it or you haven't heard of it, this is how biological neuron it's built. I think this is a simplification, of course. I'm no neuroscientist. I am no biological expert at all. Like, I mean, this is the most I know about biology. But we can think of this as the neuron. This is the cell body. And give me a second. I need water. Great. Okay, let's continue. This is a cell body. It has dendrites, which are like the connections from other networks to the dendrites. We have axons, which is like the output from the cell body to other neurons, and synapses. You probably heard this before, even if you haven't heard. Sorry, even if you haven't heard of neural network fields or artificial neural networks. We heard this phrase or this word a lot in TV and in movies and stuff. You know, when you learn something, they tell you you make synapses. It's just a connection here. But I think the text has a better way to explain it. Um, the artificial neural networks discussed in this text are only remotely related to the biological counterparts, and this is a great thing to have in mind. They only inspire by, but they don't actually work exactly like the biological counterpart. And in this section, we will describe those character brain functions that we have inspired the development. Um, we mentioned that the brain consists of a really large number of neurons, highly connected between them. For purposes, these neuron connections have three principal components: the dendrites, the cell body, and the axons. The dendrites are tree-like receptive networks of nerve fibers that carry electrical signals into the cell body. The cell body effectively zooms and adds the threshold to these incoming signals, and the axon is a single long fiber that carries the signal from the cell body to the other neurons. So at this point, and if you think as in a computational way or engineering way, let's call it that way, we can think of the input as the dendrites, the cell body as the function, and the axon as the output. You know, the point of contact of an axon of one cell and the dendrites of the other cells, it's called the synapse, right? So it's range of the neurons that trains of the individual synapse, determined by a complex chemical process in the biological way. We in our neural networks are not going to do that, but you can imagine. So that is the introduction of the artificial neural networks. Let's see how this translates to the neurons we are going to use. And if you want, take a screenshot of this, or if you already download the book, that will be better. But I will need you to have this in mind. And I see a comment here from Shimari. When you learn something new, a synapse connection is formed. The more you go over the same information, the stronger the synapse connection gets. Very simplified explanation. Yep. Thanks a lot for sharing this. Okay, let's go then to how this translates to real, not real, sorry, artificial networks. And a little about notation here, but don't worry, I will explain. Here it's our neuron model. This will be a single input neuron. What does that mean? Imagine your neuron, the biological one, doesn't have a lot of dendrites, but it only has one dendrite. It talk and it was mentioned that it's like tree form root that connects many other inputs to the cell body. For simplifier reasons, we are going to just think this as just one input. This single input neuron is shown here in this figure, and P, it will be a scalar. multiplied by another scalar weight to the form WP. And here we introduced another term that is not from the biological inspiration, but we at some point realized that we needed to add another term, which is the bias. You probably heard of these terms before. Even and another reason, now I want to talk about this. Another reason why I wanted to give this session, it's because a lot of people were doing like uh, artificial intelligence stuff already. Like applying the models on TensorFlow or PyTorch or stuff, but we didn't get the idea or the core idea of how these models were functioning. Even I did before, like training neuron and training networks and models and big convolutional and transformers and stuff that perform artificial intelligence, but I didn't get the core idea in that. So for you to have that in mind, and to the next time you apply these complex networks to do artificial intelligence, you will know like, oh, they are using neurons, and a neuron look like this. So this is the explained situation here. So again, we introduced the bias. Sorry, I wanted to mention that. Um to pass to the summer, uh, and that comes to an n output that goes into the transfer function. Again, a concept that you probably heard before if you are doing these artificial intelligence things, just like in the higher level. But here we will talk about the transfer function more deeply. So all of that translates into this figure. We have P that multiplies to W with a summing, and the summer uh, output we will call N. It's affected by the bias. How? Well, we add all of this. And then we applied the transfer function to N. N, you can think of N as this one, WP plus B. And A, we will know A as the final neuron output. So, for instance, let's think an example. We have a weight of 3, an input of 2, and a bias of minus 1.5. So, transfer function, we will leave it as just transfer function, will be a function applied to the value 2, 4.5. Because 3 times 2 is 6, and I don't need to tell you what is less than 1.5. So, yeah, this is how the neural looks. It's not complex. Actually, it's a very elegant simplification, fancy for what a biological neuron should look like. So, remember, we talk about dendrites, the cell body, and the axon. The axon will be what A is. The dendrites will be like P is. And the cell body, it's all containing the things inside the neuron. These brackets, the neuron. So now you have this. Let's continue to what the transfer function is. And the transfer function, it's just a mathematical function to tell us what the output should look like. And it is very important because depending on the transfer functions, it's so important that actually neurons take their names based on the transfer function. So, for example, this will be a Harlem neuron, or this can be a Purling neuron, you know? We have a variety of transfer functions. Actually, right now, there are many, 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 many. One very popular at the moment, and you probably heard of it, it's ReLU. And there are ReLU variations all over papers, like with the joke of, for example, JavaScript having one new framework each day. Well, we have ReLU varieties once a week. Like they release new transfer functions and many many times. Um, but again, if you were wondering what these transfer functions are, it's simple. It's just mathematical functions that tries to scope the output of the neuron. So we have a set of the firsts and the I won't say the most commonly used because again they are very very new um, transfer functions that have proved that it works better for some cases. But for example, when you want to classify and in this case we want to talk about the perceptron, we have the hard limit, you know, and this can help you to get a binary output of your network or of your neuron, because every value that is more than zero will be set to one, and every value that is less than zero will be set to zero. So you get a binary output out of it. That it's the main purpose of this transfer function. We have another one that's called the pure linear. So what you get from the input, you get from the output. And I'm talking not about the neuron, I'm talking about n. So if you get whatever in n, and you pick the purling function here, whatever you get on n, you will get on a. So that's just like that. We have more. We have log sigmoid. We have hyperbolic tangent, daxing, positive linear, and well, this you can get another time a screenshot of this, have it in your room, like cheat sheet or something, because it's very very good to have. Symmetric saturated linear is very similar to Halloween, except that there's a little scope in the middle that it's like purling, like a combination between purling and hardening. How we know which function we should use? This is a very very good question, and I will tell you that network architectures already come with functions. You know, um, for example, again, for this one, we are going to do review today. The Hamming network. Hamming network. It's a network architecture that has two layers. That means two cells connected, two neurons connected, and in the first neuron we have, or I need to remember, but I think it was purling. So You have purling in the first network, in the first neuron, and in the second one I think you have puzzling, but I will have to review. I don't want to like the thing is that I didn't decide it. I want that one transfer function or another in the in the architecture. The architecture already comes with them. If you want to do a new architecture, that will mean that you have to prove in a paper, do research, and do a lot of stuff that with that design, it works. It's a very, very good question because it's not an easy answer. It depends on what you want to do. It's more common to see, for example, again, Harlem and Harlems, which is the symmetrical of Harlem, for classifying mode. You know, like if you want to create a network to classify, and there are networks that can do both. Like they can classify and they can predict. For example, this Hamming network I'm talking, it cannot predict. It's a network that it's built just to classify. Same with perceptron. You can't predict. But then you have other line, which we will review, that you can have both modes and in the same and in the same network. You know, and that's where it starts getting really really beautiful. And yeah, it will depend a lot on practice. You will see the output, and you will see that this is where the artistic phase of engineering comes up, because designing it's led by patterns, it's led by rules, but all designs, all types of designs, you can call it web, you can call it drawing, you can call it sketching, you can call it building. While in this design of the network, you will have to put a lot of art, or you need to get artistic on this. But yes, short answer will be it depends on what you want to do. If you want to have classify, if you want to predict, and you will see, for example, if you want to get an output of a neuron that connects to the next one, what you need. If you need a bounded output, like from 1 to 0. If you want it just completely, just reducing the size, for example, you can have the log sigma. If you just want to get positive values and get rid of all negative ones, you can get the puzzling and stuff. Thank you. No, you're welcome. So that's it for the transfer functions. And I know that you probably have many questions like this, but let's start getting into the code to see if more questions are answered by me. Um, just finishing this, I wanted to mention that the single input neuron is not at all common. You will have multiple input neurons, right? And before getting into the Hamming one, I would like to review these multiple input neurons and neuron architectures with more than one neuron and with more than one layer, because that will be a great thing for you to have in mind for this Hamming network. So typically, sorry, a network has more than one input. A neuron with R inputs is shown here. So R will be the size of the inputs. Later, we will see that we will introduce S, that will be the number of neurons. Sorry, yeah, the number of neurons. N will be that, B will be that, and A will be the same. So, one neuron, multiple inputs. See how this changed from the previous one. Because now it's capitalized and in bold the W. This means now this W, it's not a scalar, but it is a matrix. And P, it's also not a scalar, and it is a vector. For the moment, we are going to work with vector inputs like that. Could we work with matrix inputs? Yeah, the answer is yes. That's for convolutional neural networks. ComNet, if you heard of that term before. It is possible. I mean, we have the tools to do it. But for the moment, for these sessions, we are going just to work with vector inputs. And for computational sake, because that can be very heavy, like working with matrix inputs. But yeah, let's continue. This is how the multiple input neuron looks like, and let's move to how multiple neurons look like. This is the same if you check it, but I think this is a cleaner way to show it. We have R size P input and 1 times R size neuron. And attention to this 1 times R, right? So, network architecture. Layer of neurons. A single layer, that means no connection between neurons. It's just more than one neuron in the layer. It's given by S. So a single layer network of S neuron is showing here. This representation will be something like the one we have here. And you will see why this one was a cleaner one. This can be translated to this. But now check that we don't have one, but we have S. Remember, one time, or well, matrix they can add. So R times one, R meaning the size of the input vector. One will be always, because right now we're just going to work with inputs with vectors. Sorry, R times one gives S times R. So the weight matrix, this will be this one here up. Weight matrix will be given by the number of neurons in the layer or in the architecture. Yeah, in the layer. Sorry. The number of neurons in the layer times the size of the input vector. So we can have P1, P2, P3, P till R, and we can have the weight for 1, 1, Y2, 1, R till S. So this it's like the spread representation, and this is the nice, simple, and compact representation of that. Meaning that, for example, if we have an input vector of 2 and just one neuron, the size of the matrix weight of the weight matrix will be 1 times 2. We have 1, 1, 2, 1. Sorry, 1, 1, 1, 2. Right? Yeah, because the left one is the neurons. If the size of the input increase, it doesn't necessarily mean we have to increase the neurons. So, very similar question what Olive asked before. How could I determine how many neurons I want in my network? Well, again, that answer it's already replied on the network architecture we want to get. For example, in the perceptron, the number of neurons in your network will be the number of classes you want to get out of the network. For example, if you just want to classify two objects, you will have one neuron. If you want to classify four objects, you have to have two neurons, and so on and so on and so on, given by the function s, number of neurons, uh, elevated to 2. So that will be the answer for perceptron, just perceptron. How many neurons for Hamming? How many neurons for Adeline? How many neurons for more complex architectures? Well, again, it will be given by the architecture, the number of neurons in your design. So if at this point you can think of the neural architectures like recipes, uh, can we have something like that? Let me check. Mm, mm, mm. So we can chain multiple functions and weights. Uh, yeah, I get your question now. The answer will be no, and I will show you why. The thing here is, remember, you have a neuron, and the neuron is already composed by an architecture. So let's return here. Your neuron starts in the inputs and ends in the output of the function, right? So for this, you mentioned that you are applying W1 times P. I'm going to show it again so people can understand me. Uh, W, which will be the second transfer function, to G will be the second transfer function, W1 times P. Here, you don't include a bias. Okay, you can omit bias. I get you that. But you cannot multiply the output of this neuron uh, to the value inside the transfer function of the second one to f. If you want to change that, it will be something like this. Let me write it for comments to you. And we will see it. Actually, having network is chain. The output of one neuron to the input to the next neuron. So you will have a more clear idea of this. But let me draw this for you. It will be W2 times P plus B it will be like this. Yeah. So that's how you change it. You don't actually have them inside the transfer function, because then it will not be a neuron. Remember the definition of the neuron, you know. And yeah, now returning here, how many neurons we have? Remember, that's for the sign of the architecture that are already built. And if you want, again, to build your own architecture, like if you want again, I was mentioning the example of the recipe. There's a recipe for doing, I don't know, let's say pizza, right? So if you want to do pepperoni pizza or margarita pizza, you are for sure you're getting something nice. You're getting something tasteful, and of course, if you're experienced enough making these recipes, at some point you will have the idea of, hey, this time I want to put how to say this, the tomato sauce on the pizza. Instead, I will add Alfredo sauce, and there will be white pizza instead of the regular ones. And the dude that came up with this idea and show it to the world, and it was like, wow, we love white pizza. We love the pizza without the tomato sauce, and instead you add the Alfredo sauce, which is just was a great idea, and we all love it. But that's an invention. That's something new. Yeah, that's how you discover things. Uh, in the case of artificial neural networks, you change weight values, you change input sizes, you change number of neurons, you change neurons connections, you change transfer functions, you start doing these crazy stuffs, but then you will have to prove that that works. For the pizza thing, the proof will be that your output pizza tastes good, right? So then you won't have to worry about that. Uh, yeah. So I hope that's clear, and you get that right. I explained myself right. Sorry. So I see that I'm 11% on my my computer. So I need to charge it. Give me a second. I will get the charger, and I'll be back. So this can be a great chance for you to take water. Give me a second, and also I need to take a quick screenshot here for Global Hack Week, for today Global Hack Week. Uh, so smile. Well, that smiles for me. Okay, let's pretend we're doing very funny stuff. Okay, I have the screenshot now. So, yeah, I'll get the charger and I'll be back. Yeah, you see it, low battery. Give me a second. Hey, sorry, it kicked me out of StreamYard. So I don't know, but hey, we're back. So uh, I want to check just very quickly if you can help me on comments to verify you can hear me and you can see me again. Um, I will appreciate that. Meanwhile, I'll start sharing my screen back again. Okay. Interesting stuff, says Storm. Great, thanks. But I do want to verify you can hear me. Everything's good with video, audio, and stuff again. So please, please, please just confirm on comments. No? Anyone? Other thing I can do is like open Twitch and see if I'm feeling good for that. Twitch. Okay. I think I see a stream in Twitch, uh, but I want just to check the audio. Well, apparently it all works fine. So we can continue. Uh, nice. So where we were. Yeah, here we're talking about the designs and stuff and how these architectures can be recipes, and in the future you can have the ability of change the recipes, and with your own ingredients even, um, as you experienced chefs knows the flavors, uh, create even a new creation, you know. Cool, amazing. So remember, here. One input, one neuron just connected. Multiple inputs, one neuron connected. Multiple inputs, multiple neurons, one layer, meaning not connected to here, connected. Multiple layers connected. And here, this is the spread form. Again, we will to watch a more compact and elegant way to represent this. But we need to have in mind something. This A1, F1, W1, B1 doesn't mean, this doesn't mean that it's elevated to 1. This means that it's from the first layer. So A2 doesn't mean the value it's elevated to the 2 or here at cube. No, this means for the second layer and for the third layer. And here it's what you were talking about, Olive. So here, for example, it's the transfer function of the whole, the value of the outputs will be the value of the third layer output, meaning it's the transfer function for the F3 times P. In this case, the P it has, the input, it's the output of the second layer. And the P of the second layer, it's the output of the first layer. So I don't see now the comments because again it kicked me out the StreamYard. But I'm pretty sure you mentioned something like this. So at this point, you're right. At this point, when you have to connect the values, and it depends how you want to connect that, because these are full connected, meaning that all the values from the first layer goes to the second layer, and all for the second layer goes to the third layer. Um, this, you can think of it as the compound function. The P for the first layer will be the P input. The P for the second layer will be the A1 vector. A1, it's these functions, so this is the functions. The P for the third layer will be A2 vector, and A2 vector is this function right here, you know? So I hope it makes sense. Here, you see we change P from A1, and the P here, it's A2. Amazing. And this is the compact way of representing that. Which I think it's more, well, both can help comprehend it. This is a spread, you have multiple lines connected there. But once you understand it, this I think can be better, since you just have the blocks and sizes of that blocks. R meaning the size of the input vector, S1 is the size of the first layer, S2 is the size of the second layer, and S3 is the size of the third layer, because it's the number of neurons. Uh, Fun thing here is, notice how you can have three neurons here, for example, one neuron in the second and other three neurons in the third layer, or four or five. What I want to mean is that you don't necessarily have to have the same number of neurons in each layer. Uh, why can we use the same bias? Another great questions. You're full of great questions today, Olive. And the point is that you can do. And what I mean is that it's the same I was mentioning here with the number of of the neurons. S1 it's different from S2 and it's different from S3, but they can have the same values. What I mean with it's different, it's that they represent different things. They represent that the weights for the first layer are a set of values that will get you an answer for that neurons. There are architectures that divides this according to the layers. For example, the perception just have one layer, so the output will be the exactly thing you wanted in binary output. But there are more complex networks that, for example, in the first layer, they identify. I need to talk about specific examples here. Let's imagine a neural network that it's designed for identifying handwriting numbers. And I'm going to take a lot of license here, but let's think of it as process. So in the first layer, you have to identify uh, sticks and circles. So your first layer identify these sticks and circles. The second layer counts the number of sticks and circles, and the third layer uh, do classified based on the number of sticks and circles. If the number is 1, 2, 3, 4, 5 to 10, well, to 9, 0 to 9. And with that information, you can say that the weights that the neurons need for doing that tasks are different. There are different weights to identify patterns if it's circle of a stick. You have different weights to identify if to count that number of circles and sticks, and you have different weights to identify the full number. And that was a really really small simplification. The process of identifying handwriting and numbers, it's more complex than that. Uh, well, same with the bias. The bias, it's a value that helps the calculating process for these operations. So remember, you multiply the input times the weight the weight matrix, you add the bias, you gather along all the data, and you pass it to the transfer function. So that's why you need different biases. I mean, they can have the same values if you want, but it's not that common. I haven't seen that much. Yeah. So that's the thing. And now I think I remember more the definition, the function definition you had before, and yeah, you were missing exactly the bias. And I told you, you can omit the bias. If you think the bias is zero, that's okay. That's good. The thing is that yeah, the thing is that normally bias it's an important part of artificial neural networks, but other times, yeah, you can omit it. And actually, in the Adeline example, which is the last one I have prepared for this series, we don't have bias because for the purposes of the scope of the intention of this series, the bias doesn't help. Actually, the computational process more complex and well, you will love that Adeline example. Oh, I think I get it. It's because the size is not constant. Not because of the size, because actually the bias you applied depends of the size of the neurons, and for each value you perform that operation. Remember, it helps. If it helps, you will see it on code as a loop, and you will see how bias affects. Oh, I got it. Okay. I hope you got it better with code. And yeah. Uh huh. Uh huh. Okay. Now we have covered the basics. You now know what how a neuron looks like, how a biological neuron looks like, how this computational or artificial neuron looks like. what a neuron with one output looks like with many outputs. A network architecture with multiple neurons that's being in the same layer with multiple neurons and multiple layers. So we have covered that, what a transfer function is, etc., etc., etc. Cool. One last things I wanted to show you, it's that we can have recurrent layers, meaning that the output of the layer can be feeding the input for the next time. And you're probably wondering how that works. Well, what happened with the input then? The input serves as first values, and see now how A it's a function depending of t. It's not time. I want to clarify that now. It is not time, but it helps. Like we're talking about iterations. Uh, T is not time. It is more like cycles. So for the first cycle, A0, the value of the output will be exactly the value of the input, you know? And for the next time, AT plus 1, uh, uh, first cycle is turning counting in 0 will be 0. Second cycle will be 0 plus 1, 1. It will be exactly the same as if a neuron received a value. It will be the input p. In this case, p it's a t, a t for the first for the second time, or for the 1t it will be a0. You know, um, p we change it for the value of the previous uh, output value. So that's why at plus 1 it's the function, the transfer function. In this case, we're using satellites. It is, again, not necessary to use specific satellites. This is just an example. That it's multiplied weight vector times p. P in this case for the recurrent layers, the recurrent neural networks are the AT, meaning the previous value of the neuron, plus B. And this is important, and this one specifically, the recurrent layer, because it's what we are going to do right now. So I'm going to introduce you. Again, we have a summary, the single input, multiple input, transfer functions, layers, many layers. Um, the delay, yeah, you can check it, integrator, but the recurrent. And again, this was an important thing because right now we are going to check Hamming example with example. With a good example, right? So the Hamming network. The Hamming network, it's an architecture of an artificial intelligence network designed to predict, to classify binary elements. And what I'm talking with binary elements, sorry, I just see the question of Olive. Is this algorithm used in self-learning AI? Yeah, that's one of the things we were mentioning before. Uh, Neural networks are used in AI because they have things um, like learning rules. So we can make a learning rule to change the configuration inside the networks to adjust for doing a task. Again, we can do artificial intelligence without neural networks, and we can do neural networks without artificial intelligence. In this session, in the 30 minutes left we are going to check exactly how this Hamming network works without artificial intelligence, because we are not going to give a learning rule. We are going to adjust weights, bias, and all parameters manually, so the network classifies correct, yeah, but we do all the hard work. We do all the designing and changing values in order to make that correct classification works, not because of the algorithm learning anything. Later, I mean, later, actually today, because three of the sessions are going to be today. Later, we are going to check the perceptron and how the perceptron learning rule works. So, yeah, in the perceptron, we are going to apply AI, because in that case, we are not going to adjust parameters for anything, but we are going to just design everything to make perception learn how to classify things. So yeah, returning here, yeah, to the Hamming network. The Hamming network, it's think uh, for classifying binary inputs. The objective of the Hamming network is to decide which prototype vector is closest in Hamming distance to the input vector. If a Hamming distance doesn't sound familiar to you, it's, for example, you have two binary vectors. You can see the Hamming distance as checking. For example, let's do this short. We have two input vectors, or two vectors with three elements of dimension 3. Well, 1 and 1. Hamming distance, both first numbers are equal. Yeah, so Hamming distance 0. Uh, the first vector has 1, 1, 1, and the second was 1, 0, 1. Okay, so first values 1, 1. Hamming distance 0. Second values 1, 0. Hamming distance 1. We increase the distance. Second value, the third value, sorry, 1, 1 again. So the result will be the Hamming distance between these two values, it's equal 1, because they only have one element different. According to this, if we have, for example, the example that the book gives us, it's a fruit classifier. So we have apples and oranges, and we have a sensor that detects shape, texture, and weight. So if the shape of these fruits, it's like sharp, clean, etc., it will give a 1. And if not, sorry, the shape it's round, right? So if it is round, it will give a 1. Uh, Apples and oranges both are rounded, right? So both have 1. If the texture decides one it's like sharp, clean, and uh, no no rough, it will give a 1 again. If not, it will be a -1. Apples are clean, like no roughness. In the oranges, you have a -1 because they are rough. And the weight between we can see, like, I don't know, if it weighs less than a kilogram, it gives a one, sorry, a -1. So for both apples and oranges, this happens. So both have a -1. Now take a look at these two vectors. This is the prototype vector of how an orange would look like: one in shape, -1 in texture, and -1 in weight. This is the prototype vector of how an apple will look like: one in shape, one in texture, and -1 in weight. If you put a lot of attention, you will see that they are pretty similar. Actually, they only change in texture. So the Hamming distance between these two, it will be just one. But let's imagine that now you introduce in your machine a not so perfect orange. You introduce a mandarin. I don't know if the word for that is mandarin in English. Okay. Yeah, no, I think it can be translated to tangerine. So yeah, you introduce a tangerine. So the question here is, what will be closer? It will be closer to an apple or an orange. Well, let's pass it through the sensors. Shape. Okay. Imagine this is not a perfect tangerine, so um, it's not round enough. It's like a highly eclipse. I don't know, something different. It has a weird shape. So the vector, it will give us -1, right? -1 texture, it will be similar to an orange, so -1 here, and it's less than a kilogram. So the vector of this classification will be -1, -1, -1. Now you take close attention. -1, -1, and -1. Which one is more similar to the orange and to the apple? Well, if you ask me, like, I'm a human, I will have to take a lot of attention here. If you ask me, a human, to classify it, I will tell you it's more closer to an orange just by intuition. But let's make that mathematical. Uh, 1 and -1. Okay, we add 1 in Hamming distance. -1 and -1. Okay, no Hamming distance increase. -1 and -1. So no Hamming distance increase. The Hamming distance between the orange prototype vector and the tangerine -1, -1, -1 is just 1 in Hamming distance. Now, for the apple, 1 and -1, we add 1 in the Hamming distance. 1 and -1, we add another 1, so we have 2 in Hamming distance. -1 and -1, no adding. So Hamming distance, it's bigger here for the Apple prototype. So the one closer to the tangerine we introduced in our sensor classifier, it's the orange. So congratulations, we classified correctly. But we are humans. We could do that just by intuition. Let's teach and let's prepare a Hamming network to do that. Now that you understand the process of how this should work, let's break it down in the components of the layers. I have to warn you, this won't work like the example I mentioned before. Like, oh, in this layer we will separate if I don't know, like if the fruit weighs more than a kilogram, and in this other layer we are going to decide which fruit it is. It doesn't work like that. I just take license to to make out an example. In this case, we have two layers. The feed-forward layer, meaning what it enters, it goes out, and the recurrent layer, you remember we talk about these kind of layers, in which the output of the first layer it's the first value of this. So the first value of the second layer it's the value of the first layer. Then we have to repeat again until we hit some response. The feed forward layer, remember, this it's like a recipe. So the weight matrix it's already given. And the recipe tells us the weight matrix for the feed forward layer should be the prototype input. Uh, this T means, remember the prototype input, it's 1XR, 1XR. This transpose T means we are going to make it, if we had a column, we're going to make it a vector. Sorry, a row vector. If we had a vector, a column, sorry, if we had a row vector, we will make it a column. That's only that. These are matrix operations. So remember the orange prototype? 1, -1, and -1. It will be the first row of the matrix, of the weight matrix. The Apple prototype was 1, 1, and -1. So this will be the second row of the weight matrix. Now, the bias. The bias is going to be given by the number of elements. We are going to create a column vector with the number of elements. In this case, we have two elements we want to classify, apples and oranges. So it will be two elements. And the value of the elements, it will be R. Remember, the size of the input. So in this case, we have 1, 2, and 3 elements per input. So that will be 3 and 3. 3 because of the value of R, and 2 trees because we have two elements. If we could, if we wanted to design another Hamming network that classifies oranges, apples, and bananas, we have to add another row here with the prototype vector of a banana. That will be, remember, this is shape, texture, and weight. For the shape, obviously, it is different. This will be a -1. For the shape, I think it can be more similar to an apple, so it will be -1, 1, and the weight remains the same. No banana weighs more than a kilogram, so this will be -1. So -1, 1, and -1 will be the prototype of a banana. And that's how the weight matrix will be affected. The bias will be affected by adding another 3 here at the end of the column vector. How we change this 3? Well, we can change it to 4 if we add another column here, not representing this was shape, this was texture, this was weight. Let's imagine this is one called color. So if it is a dark color, it will be -1. If it is a light color, it will be 1. I don't know, something like that. So in this case, we have 4, 4, 4 because we have a banana. That's how this is defined. And the feed-forward layer only applies one time because we just need one A1. It will be W of 1, the weight 1 matrix, P, which is the input for the whole neural network, and B1, which is the ones we defined.
So remember, this one doesn't mean it's elevated to one. It means it's the weight matrix for first layer. It's the bias for the first layer, and that's it. So that's all we need to know here for the feed forward layer. Now, recurrent layer, it's a little bit more complex. Remember, A2, the first, because this is zero, the first output of the second layer, it will be the first layer. This it's called the initial condition. And the next times the recurrent layer starts generating, we are going to give A2 time t plus 1. It's equal to puzzling. This is the function. Oh, remember the transfer function for feed forward layer? I think we didn't mention. It's purling. So whatever comes in comes out. So this is why we're not mentioning it here. This was omitted, but this doesn't mean you have to, or you don't have a transfer function. So remember, purling takes all what it's in to to the output. So that's why you can say it's like multiplying to one. Yeah, exactly. But we have a transfer function. We cannot define a neural network without a transfer function. That's very, very, very important. Uh, in this case, for mathematical output reasons, we don't mention it. Like there is no pure link here. But remember, having your mind, you have pure link, right? Cool. So yeah, returning. Sorry to the previous one. Sorry to the recurrent layer. You have puzzling, the weight matrix of the two. Sorry, the weight matrix of the second layer, which is this recurrent layer. The P here, it will be the output of the layer in the previous value. And the weight. Here, how the weight is defined. Sorry. Well, the weight matrix for this second layer, it's defined as this. Uh, we will have a diagonal of ones, and in any other value, and I mean in this case it's because it's 2 times 2, because we only need to classify two elements. If we wanted to classify again the third element, we have to make this at 3 times 3, and any other value that it's not in the one diagonal, it's going to be minus epsilon. But what is epsilon? Epsilon, it's a number less than this rule. 1 divided in s minus 1. Remember, s is the number of neurons. In this case, we are doing 2 neurons because we want to classify 2 elements. And yeah, that's it. There's a section in this book where they give more attention in proving why this works, because this is kind of odd, like for example, oh, I thought it was olive with an L. So sorry, man. Oive. Oive. I think it's oive. So sorry. Um, YW is defined like this in puzzling. Yeah, exactly. That's what I was mentioning. This is because by many resources, the designers of these Hamming networks proved mathematically that this works, and this gets to converge to the function. Um because that's the other thing, since we are recurring, we're making loops every time and every time and every time and every time in this recurring layer. At some point you have to stop, so we have to indicate stopping criteria. One can be number of iterations if you're talking in a code. Then you can say if you complete the criteria of having two times the same output, and three, the criteria of having an evolution, because it is also possible at some point that you perform the changes, but you don't have evolution over the results. So there is let me get if I can reply to you xpdk asun why w is defined like this in the puzzling. Well, w is defined. Oh, Rosendo, you're here. Yeah, I'm wrapping up. Just give me a second. W is defined like this because of the inventors, again, came up with this solution with mathematical reasons. The proof of that is discussed in later chapters, but for the moment, trust the recipe. For this recipe, the weight matrix will be defined as this. If you want to increase the number of categories you want to classify, then you will have to add more epsilons in the corners and increase your one diagonal, right? Now, take attention to something we were mentioning before. We don't have a bias here. We just have weight matrix multiplied by the previous output. So you can assume in this moment that the bias, it will be zero. So same with the puzzling, uh, with the purling, like it's multiplying to one. Well, not having a bias, it's like adding a zero, but you have it. You know, uh, for design here, it doesn't make sense to have a bias, so bias it's zero. And well, um, once we have the weight matrix, we can see that the output is defined as the puzzling plus the weight matrix of the second layer to the previous value of this same layer. Remember, for the first time this happens, the initial conditions tell us that A2 is going to be A1, the output of the previous layer. For the next time it happens, it will be A1 puzzling weight matrix A2 of 0, which is A1. For the next time it happens, now it starts getting the values from its own. So it will be A2 puzzling W weight matrix of the second layer, A2 1, which was the previous value, and so on, and so on, and so on. Theoretically, can we set matrix automatically? For example, okay, this is not helping. Um, for example, as you said, if we want to add new quality example, color, weight, yeah, actually, we do that. We need to do that. It will be the best practice. Can we add equality using model. If the model thinks that apple and orange have other qualities, it makes added value to matrix and to multiply. Okay, we're running out of time, but remember, this is going to be a four serious sessions. So I will see you later. Let me check when, like in a couple of moments. Don't worry. Um, Part two, it will be 3 p.m. ET time. So uh, you have been an amazing audience. I love all the questions that you're throwing. Oib, I hope to get back to you, and if you can't watch live the second part, I will answer that question. Don't worry, and you can watch the recording later, and also all the questions that I have left. Right? Okay. Yeah, because we're running out of time. So, but don't worry. That's why this was a series of four, because I know it needed time to develop all this knowledge. Right. So, thanks a lot for joining me, and I will see you for today in Global Hack Week Day 4 at 12. I don't know if it's PM or EM. That's a great question. Let's call it just 12 at the time, and then we can come back to the part two of this series of neural network design. Right. So, see you. Thanks a lot. I will answer these questions that you post here. So, thanks. Bye.